first part of this chapter, chapter 13, 13:1, 2, 3, are basically review of what we did way back when. I'm not really sure why that's so, but we'll go over this real quick. We talked about the different types of beams back when we were dealing with beams early in the semester, right? So there are the different support types. Roller, again, no resistance in the X, and this is showing your reactions. But there is a resistance against the weight of the beam plus the gravitational pull, right? Pin or a knife edge. Okay, if it's pinned, it can't go left or right or up or down. I guess it could go up in that case. Well, actually, if it's pinned, it wouldn't be able to, would it? But the reaction will be over at that pin. The reaction most of the time will be going up. Won't always, but sometimes. And then you have the fixed application there, where that beam is protruding out of a wall or something. And note now you do have an X and a Y, and then you also have a moment reaction there. So keep that in mind. Okay. Let's see, different things. What do we want to say about this one? This is figure 13.2. The different types of beams. So you've got the simple beam, simply supported, if you will, supported on both ends. A fixed beam. Okay, now note there's a difference there, isn't there? They're both fixed per se, but there's no moment going on at either location there on the reactions on the simple beam, but the fixed beam there is, or can be. Let's put it that way. Cantilever beams, and they're actually showing that cantilever beam sticking out of the wall. That could also be a situation. Do they have one? No, they really don't have one. But a cantilever beam could also be like this, where you have your beam going across here, and you might have a pin reaction here, and then you could even have a roller reaction here. It's cantilevered on both ends. Okay, so that can happen, right? Nothing wrong with that. So that's another. Do what?
Is it either or is it both?
What? It could either be this or that, yeah. As long as it's. Do what?
That's not a roller and a pin?
No. It could be any of that. It could be any combination. It could be something like this, where you might have a pin here, and then you might have your roller all the way out here. Okay, and this is still cantilevered. It's just when the beam is sticking out there and is unsupported, if you will. Okay, so that's what's going on there. All right, and this, obviously, that's cantilevered out as well. So think in terms of a diving board type application, especially since we're talking about the Olympics, right? We haven't been talking about the Olympics, but that is a cantilevered beam that just happens to be springy in most cases, although the fixed platform isn't, is it? But, let's see. What else they got there? Does that say propped? I can hardly read it. Propped cantilever beam. Okay. That's fixed on that one end, and then it's got that roller application. Overhanging. And that's, I guess they're calling it an overhanging. That's always been a cantilever beam to me. Then you've got the continuous beam, where it's just got different supports on it. Okay, now, and other than the fact that these forces are all going straight down, I don't know why you wouldn't have a force on the X there. I guess they're not showing any X's on those. So you do have the potential to have an X on those, but they're not showing any of that. Okay. What do we have here on this types of loads? Okay, so we've got a concentrated load here. Again, this is stuff that we've been doing early in the semester. We have concentrated load here, uniformly distributed load, which ultimately we turn into a concentrated load, don't we? Like kind of right there in the middle. Okay. And then we have non-uniform distributed load, and that could even be just just one triangle. Here they've shown it both triangles. Okay, so in fact you'll see that as we move along through this chapter, you'll have some applications like that. So here we've got a beam diagram and then what the load would actually be, and this is kind of what I was just referring to. Here you've got, and I would go one step farther, and my free body diagram would look something like this, wouldn't it? Where you've got probably some kind of an AY, potentially an AX. You've got the weight of the beam, it says, is 1 kip per foot, so it's 40 feet long, so it's 40 kips here, right? Then we've got a 5 kip force. And then we've got just the BY. BX is 0, right? Of course, if we were doing our free body diagram, we'd have to put some distances in here, wouldn't we? That's going to be 20 feet. And this would be what, 32? And of course this would be 40. Okay, so do you remember how to solve for AY and BY? Remember, if we just wanted to solve for AY and BY, we don't really need to go through the forces in the X and the Y here, do we? I mean, you could. The forces in the Y would be what, minus 45? Kind of, sort of, just for those two, but you still have to have AY and BY. But you could just, to solve for the moment at A, sum the moment at B equals 0. Well, let's see if we take it from B. This is going to be, what, 5 kips times 8 feet. And that is positive, right? It's going counterclockwise. Plus 40 times 20. Minus AY times 40. So AY would be what? There's 40. And what's that, 800? 840 divided by 40. What's 840 divided by 40? Divided by 4 would be 210 maybe? 21? I'll fix it. 21.0. How's that? A little recovery. And it is going up, right? And that would be kips. Okay. So, then we could solve for BY just the same way. We'd just have to go through A. But can we? Yeah, we couldn't really solve for BY any other way at this point, could we? Sum the moment at A. Then we would have 40 times 20. And that is negative, isn't it?
You just do the sum of the forces at this point, couldn't you, to find the BY? Because it'll have to add up to...
Yeah, it would be, what's that, 45 minus 21? Yep. Let me finish this though real quick. Let's see, then we've got, and that's negative, then we got minus 5 times 32. They should be the same, right? Plus BY times 40. So BY equals whatever, and then like Clark said, sum the forces in the Y, equals 0, we had AY be 21 minus, was it 40? Minus 5 plus BY. BY equals 45 minus 21. Kips up. And that's what that should equal to, right? So, just a little review there. What do we got? What else we got here? Now the next one we're showing here is a beam diagram. Are we really doing anything different there? Beam diagram, load diagram, really there's no difference there, is there? You're just looking, now the only difference is on a free body diagram I wouldn't put all these arrows in there.
I guess you're.
What? Yeah, they're showing the 60 kilonewtons here. That came a result of 12 kilonewtons per meter and 5 meters, right? In the 5 meters, you can figure that 5 meters because this is 10 and you're taking away 5. So this left over right here is 5 meters. Okay, so that means you got 60. It's right in the middle. Now that'd be the only thing that would be a trick is from A, it's actually a half a meter over to the right, isn't it? That would be the only tricky part. I have seen test questions like that before. Just saying. You know, just in case. You always have to pay really close attention to that kind of thing. You don't want that to jump up and get you, which will just get you for a couple points. So